This is problem 9-143. It's on page 548. A turbojet aircraft is flying with a velocity of 320 meters per second at an altitude of 9,150 meters, where the ambient conditions are 32 kilopascals and 32 degrees Celsius. Negative 32 degrees Celsius. The pressure ratio across the compressor is 12, and the temperature at the turbine inlet is 1400 Kelvin. Air enters the compressor at a rate of 60 kilograms per second, and the jet fuel has a heating value of 42,700 kilojoules per kilogram. Assuming ideal conditions for all components and constant specific heats for the air at room temperature, determine A, the velocity of the exhaust gases, B, the propulsive power developed, and C, the rate of fuel consumption. Okay, so let's see. We've got an ideal jet propulsion cycle. Let's draw a TS diagram for it. It looks a lot like the Brayton cycle. In fact, the Brayton cycle is where we start with the turbojet cycle. The only difference is that now, instead of just having the compressor and the burner and the turbine, we now have a diffuser and a nozzle. And the whole purpose of a jet engine is to generate the high temperature gases that are being pushed out of the nozzle. That's the whole point of the jet engine. Now, we're given a few things. The temperature at the inlet to the engine is negative 32 Celsius. I'm going to go ahead and just convert that to Kelvin and write it down. It's 241 Kelvin. The pressure at state 1, or on the low pressure side, is 32 kilopascals. That's the local atmospheric pressure. You have to be careful here. The pressure ratio across the compressor, okay, across the compressor, what's that? Well, that's right here. The pressure ratio across the compressor is 12. That's not the pressure ratio across the cycle. That's just across the compressor. Now let me sketch the aircraft as well before I continue with the cycle. I'm out of space here, so I've got to squish it down. So there's 9,150 meters, which is the cruising altitude for this aircraft, okay? There's my best aircraft. It's moving along at 320 meters per second. Okay, what else did they give us? They told us the maximum temperature, or essentially the temperature going into the turbine. That was 1400 Kelvin. And they told us the heating value of the fuel, which relates to Qn. In fact, the heating value of the fuel is 42,700 kilojoules per kilogram. And what else? Well, they told us the mass flow rate of the air, and that was 60 kilograms per second, which is a pretty decent flow rate. I mean, air is not very dense, especially at this altitude. To have a person's mass of air every second, essentially, or a light person's mass of air flowing through this engine is pretty impressive. Okay. So how do we solve this? Well, essentially what we're going to do is walk around the cycle diagram, solve for the various states, and see what we can do. So let's go from state 1 to state 2. Now, this is an isentropic or ideal cycle. So 1, 2, and 3 are related isentropically. 4, 5, and 6 are related isentropically. Now, if I want to go from state 1 to state 2, the only thing I have two things. I could use an isentropic relationship. One of the three isentropic equations that relate temperature, volume, and pressure, but I really don't know anything about what's going on here. So I'd have one equation and two unknowns, and that wouldn't really help me. I could also use an energy balance from state 1 to state 2, and it would look like this. Basically says that what comes into the diffuser of the jet aircraft is enthalpy and kinetic energy. Oops, I meant equals. And what leaves the diffuser section is enthalpy and kinetic energy. You should go and look at the cycle diagram as well as the engine layout in your book to understand what sections this is. Anytime you solve a problem like this, you should do it. Now, ideally in a diffuser, what happens is the kinetic energy leaving the diffuser is zero. In other words, all the kinetic energy is converted into flow and thermal energy. So that's the ideal situation. What that would mean then is that H2, let's see, let's put everything on one side of the equation. 0 equals H2 minus H1 minus V1 squared over 2. Okay. Now, if we approximate this section as Cp T2 minus T1, because we're allowed to use constant heat capacities for this problem, then we essentially have a relationship between T1 and T2. Okay. So now we can calculate the temperature in state 2. This is good because getting the temperature in state 2 basically solves state 2. So let's do that. So the temperature in state 2 is 241 Kelvin plus, now what is V1? Well, V1 is the velocity of the air coming into the engine. How fast is air coming in? Well, at 320 meters per second, because that's the speed at which the aircraft is moving through the air. So 320 meters per second, quantity squared, because we have to, over 2 times the heat capacity of air. Well, the heat capacity of air at constant pressure is 1.005 kilojoules per kilogram per Kelvin. Now that doesn't really help us much because here we have meters squared per second squared. Here we have kilojoules per kilogram per Kelvin. How do we resolve this? Well, hopefully we want to get Kelvin out of this whole thing, right? So there's 1 kilojoule, let's do it this way. There's 1 kilojoule per kilogram per each 1,000 meters squared per second squared. So see how the meters per second go away, or the meters squared per second go away, and so do the kilojoules per kilogram. We're left with 1 over Kelvin, so we're just left with Kelvin now, finally. So the temperature, I won't write it down there, let me just pull it across over here. The temperature in state 2 comes out to 291.9 Kelvin. That's just the result of that equation over there. Well, that was nice, because now we should be able to find out the pressure at state 2. How? Well, now an isentropic equation relating T2, T1, P2, P1 would look like this. Now I've rearranged one of the first, second, or third isentropic equations. I can never remember which one's which. I think this is the first rearranged. Maybe the second. No, it's not the third. But look in your book. And this is the isentropic equation that will help us, because notice all we have to do is multiply both sides by P1. And now we have an expression for finding the pressure in state 2. Because we know that the pressure in state 1 is 32 kilopascals. Now we know the temperature in state 1, 291.9. We know the temperature in state, in state 2. We know the temperature in state 1, 241 Kelvin. So we can solve it. So it's pretty simple, right? P1, 32 kilopascals. T2, 291.9. T1, 241 to the power of K, which is 1.4 over 1.4 minus 1. 1.4 is just the ratio of heat capacities for the air. Okay, so plug all this in, you'll get the pressure in state 2. So when I calculated the pressure in state 2, let's see, how about if we do this? What about if I make a table over here? State 1, 2, 3, 4, 5, 6. Here's our state numbers. Let's see, I don't know if pressure is the only thing I'll need or not, but I've got enough space for plenty of things here. We know the pressure in state 1 is 32. Pressure in state 2 we now have, I didn't tell you the number. Anyway, it comes out to 62.6 when you plug numbers in over there. Okay. Now how about state 3? Well, state 3 is easy. P3 and P4 are the same thing, all right? The pressure at state 3 and 4 are the same. So once we find that, we'll be okay. But we could simply take the pressure in state 2 multiplied by the pressure ratio. Because remember, the pressure ratio is given from state 2 to state 3, which is across the compressor, okay? Since the pressure ratio is 12, all we have to do is take 62.6 and multiply by 12. When you do that, you'll find the pressure in state 3 and the pressure in state 4. That comes out to 751.2 kilopascals. Okay. Now, could we find the temperature in state 3? We need the temperature in state 3 as well. That's how we solve the states. So could we move from state 2 to state 3? Well, sure, we could. The relationship would just be an isentropic relationship to get at T3. Because look, 2 and 3 are isentropically related. And so, this would be T2 times P, why did I write it that way? I made a mistake in my notes, but that's okay. Would be P3, let's see, divided by P2 to the K minus 1 over K. All right? Let me double check myself, make sure all of that makes sense. 3P2, yeah, that makes sense. Okay? So T2 we know is 291.9 Kelvin. P3 over P2, that's just the pressure ratio of 12. And then I need to raise that to 0.4 over 1.4. Okay, again, the ratio of heat capacities. So that gives us the temperature. Plug in the numbers to your calculator. You'll find the temperature in state 3 is 593.7 Kelvin. Okay? Now we already know the temperature in state 4. That was given. Okay? So what could we do to continue around and go from state 4 to state 5? Okay, notice we have the pressure at state 4 as well, so really it is completely solved. States 1 through 4 are completely solved at this point, temperature and pressure. How do we go then from 4 to 5? Well, here's the key. Here's something that you haven't seen in any of the other cycles. The work output of the turbine in a jet engine like this mainly goes to driving the compressor. For all practical purposes, all of the work output goes to driving the compressor. And so what that means is that the, let's write it this way, the turbine work equals the compressor work. And what that means is that the enthalpy drop across the turbine is equal to the enthalpy rise across the compressor, H3 minus H2. But we can do a CP delta T type of thing here to get rid of these H's and say T4 minus T5 is T3 minus T2. This allows us to solve for T5. T5 then is equal to T4 minus T3 plus T2. That is T5. Okay? So now we've got all of the temperatures 4, 3, and 2, and we can calculate the temperature in state 5. That comes out to 1098.2. Oh, whoops. I tried to put a temperature in the pressure. Let's put it over here. 1098.2 Kelvin as the temperature in state 5. Okay, so now what? Well, we'd also like to get the temperature at state 6. Now notice we know the pressure in state 1, we know the pressure in state 4. And the pressure in state 1 is the same as the pressure in state 6. So we can do an isentropic or use an isentropic relationship from state 4 all the way to state 6. So essentially what we're going to do now is move from 4 to 6. Okay? So if we do that, T6 equals T4 multiplied by P6 over P4 to the power of K minus 1 over K. And what do we have? Well, T4 is 1400 Kelvin. We know P6. P6 is the same as P1. I could have written it down and forgot to. Okay. So let's see, that's 32 over 751.2 to the power of K minus 1 over K. That gives us the temperature in state 5, or state 6, excuse me. So the temperature in state 6 can be calculated from that, and it comes out to 568.2 Kelvin. If we really wanted to, we could calculate the pressure in state 5, but it doesn't affect us. There's no need for it, so I'm not going to bother with it. What we really want to know are things like the velocity coming out of state 6, the propulsive power, and the fuel flow rate. So the pressures really don't matter in state 5. In fact, it might be a good exercise for you to go and try to find it. How would you find it? Well, you'd use an isentropic equation to go from 4 to 5 that relates the pressure in state 4 and the pressure in state 5 to the temperature in state 4 and the temperature in state 5. So that would be a good challenge for you to try. Anyway, to calculate the exiting velocity, what we're going to do is use an energy balance to move from state 5 to state 6. Because the process from state 5 to state 6 occurs in the nozzle, and that's where the velocity, or essentially the kinetic energy that comes out the back of the jet, is generated. So how would it look? Well, the nozzle would have enthalpy and kinetic energy coming in. That would be equal to the enthalpy and kinetic energy leaving the nozzle, at least ideally. Of course, nozzles would not be isentropic, and so we wouldn't get as much kinetic energy out as we would like, but we're approximating. Also, we're going to approximate the kinetic energy coming into the nozzle out of the turbine as 0. Okay, so rearranging this, 0 equals H6 less H5 plus the kinetic energy out at state 6. This is the same thing as Cp, T6 minus T5 plus V6 squared over 2. Okay. And so we can solve for V6. It's the square root of 2 Cp T6 less T5. And then plugging in the numbers, it's worth seeing this. 1.005 kilojoules per kilogram per Kelvin for the heat capacity. Okay, T6, 1098.2, T5, 568.2. These are both Kelvin units, and what you notice is we've got a problem. While the Kelvin units will go away, square root of kilojoules per kilogram does not sound much like a velocity. So we need to add in a conversion factor here. I don't have room, I'll run off the video. Times 1,000 meters squared per second squared per each kilojoule per kilogram. So that way those go away, and we've got square root of meters squared per second squared, which gives us meters per second. So anyway, that gives us a speed V6 of 1,032 meters per second. So that's the velocity coming out the back of the engine. We can now calculate the propulsive power, which was requested as well. The propulsive power, W sub P, is equal to the mass flow rate of the air through the engine times the velocity change across the engine multiplied by the velocity of the craft. Okay? All right. So if our reference frame is the aircraft itself, we know that the aircraft exit velocity we've calculated here is the exit. Now, let's think with me for a minute. We assumed that the kinetic energy coming into the nozzle was 0. What we're really saying is that that air was not moving with respect to the nozzle. So the reference frame we've selected so far for the nozzle is the moving aircraft. Therefore, this velocity that we've calculated, this 1,032 meters per second, is with respect to the aircraft. So if we take a difference here, we have to have both of these with respect to the aircraft if this one's going to be with respect to the aircraft. Now, V1 with respect to the aircraft, now let me plug in the mass flow rate first, that's 60 kilograms per second. Okay, but V6 with respect to the aircraft is 1032, V1 with respect to the aircraft is 320, and both those are meters per second. The velocity of the craft, this has to be with respect to ground. It doesn't make sense to say the velocity of the craft with respect to itself is 0. We'd have 0 propulsive power. That doesn't make any sense. So with respect to the ground, the velocity is 320 meters per second. Notice we've got meters squared per second squared. Okay, so what we can do is again use our conversion factor of 1 kilojoule per kilogram per each 1,000 meters squared per second squared, and that'll take care of the meters per second everywhere. Okay, and then the kilograms will go away. We'll get kilojoules per second, and everything's good. This comes out to 13.67 kilowatts. You should probably take that 13.67 kilowatts and convert it to horsepower so that you will be impressed by this jet engine and its power output, because that's a heck of a power output. Anyway, and remember that's 13,670 watts. Okay, so for the last part, what's the mass flow rate of the fuel? Well, the mass flow rate of the fuel is related to the heat flow rate in, which would be equal to the heating value of the fuel multiplied by the mass flow rate of the fuel. Now this is looking at the heat value coming in, or the heat transfer into the system, based on what the fuel is doing, or based on how much fuel is being burned. Okay? So we can rearrange this and say that the mass flow rate of the fuel is equal to the heat transfer rate in divided by the heating value of the fuel. Now, what about Q dot N? How can we get that? Well, what does the fuel do? It heats up air, right? It takes the air from state 3 to state 4 at a rate of 60 kilograms per second. So do you see that this is just the mass flow rate of the air? Let's make a little A on I should have had one there, as a subscript, multiplied by the enthalpy change to state 4 from state 3. Okay? Now, of course, instead of using H4 and H3, we're going to use Cp delta T. So Cp T4 less T3. So essentially what the fuel does is it increases the temperature of the air from state 3 to state 4. That's what it's there for. That's its job. Okay? So finally, plugging in all the numbers, we've got 60 kilograms per second of airflow. You have to be careful. We've got two mass flow rates here. One is the mass flow rate of the air, the other is the mass flow rate of the fuel. You need to not get them confused. The heat capacity of the air is 1.005 kilojoules per kilogram per Kelvin. There we go. And T4 is 1400 Kelvin. T3 is 593.7. Those are both Kelvin, so now the Kelvin goes away. The heating value of the fuel, 42,700 kilojoules per kilogram. Takes care of the kilojoules and kilograms. We're left with kilograms per second, but now we're talking about kilograms of fuel. Where did that happen? Well, this is kilograms of fuel, whereas this is kilograms of air, and so that's where that conversion happened. Okay? So really what happened is this kilogram crossed off with this one, not that one. That way we're left with kilograms of fuel per second. Anyway, this comes out to 1.14 kilograms per second. Now another thing you can do, you can actually calculate the propulsive efficiency. Because if you take Qn as this number, Q dot N, then the propulsive efficiency is equal to the propulsive power divided by the heat flow rate in. I'll leave that as an exercise to you to calculate the efficiency of this engine.